Okay, here's a problem that I want to do involving two skiers behind a boat. And you have the ability to print this out as is in your notes. Two skiers, S1 and S2, exert forces of 500 newtons and 600 newtons on a boat as follows. Find the resultant force acting on the boat and its direction. Well, as you can see, I've drawn the boat where we're sitting here. Here's my positive x-axis and so on and so forth. To find out the resultant force acting on this boat, what we're going to need to do is determine what the vector for skier 1 looks like and what the vector for skier 2 looks like, and then sum those together. So skier 1, which I will call S1, is going to be, and let's see what we know, because we have three ways to write a vector. If we know its initial and terminal point, which we do not. If we know a direction vector, a vector in that direction, and its magnitude, well, I know its magnitude, but I don't know a vector in that direction. But I do know the third way. That is, I know the magnitude, and I know the angle that it makes with the positive x-axis. So starting with skier 1, that means it is going to be the magnitude of the force, which would be F1, times the angle, the cosine of the angle that it makes with the positive x-axis. Now look here. It doesn't make a 45 degree with the positive x-axis. It actually makes a 135 degree angle with the positive x-axis. And then we'll take F2 times the sine of that 135 degree angle. So this is going to give me 500, and then the cosine of a 145 degree angle is a negative square root of 2 over 2 of 135, excuse me. And then 500 times the sine of 135 degree angle, which is a positive square root of 2 over 2. Now this is a word problem, so eventually we will round, but we're not going to start out rounding, because if we start out rounding, by the time we get to the final result, our answers are going to be too big, or we're going to have too much error in them. But I don't need to, because this will cancel out nicely, and I get a negative 250 square root of 2 for the first component, and a positive 250 square root of 2 for the second. And that totally makes sense, because in order to write this vector, it would have to have its terminal point in the negative x direction and the positive y direction, and that makes total sense. Let's go ahead and do our second skier. Our second skier is going to, we're going to use its force, which is 600 newtons, times the angle that it makes with the positive x-axis, which is actually going to be a 210 degree angle. So 600 newtons times the cosine of a 210 degree angle, and then the magnitude, which is 600, times the sine of a 210 degree angle. And so this is going to give me 600 times the cosine of that angle is a negative square root of 3 over 2, and the sine of that angle is a negative 1/2. So I will get the vector having components negative 300 square root of 3 and negative, negative 300. And again, if you think about where that vector has its terminal position, it makes sense, because in order to get to where that vector ends, I'm going to have to go in the negative x and the negative y. So my final, or my resultant force acting on the boat, we'll just call that a capital F, is going to be the sum of these two angles. And I apologize, I'm not using my angle notation, my vector notation, the sum of these two vectors. So it is going to be the vector that has as its first component, because we simply just add the first components and add the second components, negative 250 square root of 2 minus 300 square root of 3 for the first component, and then a, let's see, 250 square root of 2 minus 300 for the second component. And it's at this point that I would probably go ahead and calculate the decimals on these. Okay, so I get for this a negative 873.17 for the first component and a 53.55 for the second component. But that's not what we're looking for. What we're actually looking for is the magnitude of that force. And the magnitude of that force is going to be the square root of each of the components squared. So it's the square root of a negative 873.17 squared plus 53.55 squared. And so when I calculate this out, I get that the resultant force acting on the boat is going to be 874.8. And that makes sense. If we go back and look at that picture, we can see, first off, that the resultant vector should be somewhere in the third quadrant, based on the way the forces are acting on that boat, and that it should be more than any single force by itself. And so at least we're in the ballpark on this. Now let's determine its direction. And this is where things get especially different from what you've seen in the past. To determine its direction, we have a couple of pieces of information that we know. Remember, our vector, by definition, we're looking for the angle. That would be the magnitude of f times the cosine of the angle that it makes with the positive x-axis, and the magnitude of f times the sine of that angle. Well, I know what the vector f looks like. In component form, it has components negative 873.17 and 53.55. I also know its magnitude is 874.8. So that should give me the first component times the cosine of theta, and then 874.8 times the sine of theta. So this actually gives me two equations, and I need to find one of those that I can use to solve for theta. The two equations it gives me are the following. Remember, if two vectors are equivalent, their components must be equivalent. So I get that a negative 8, I'm sorry about the color there, a negative 873.17 will be equal to 874.8 times the cosine of theta, which I could then use to solve for the cosine of theta. To do that, you would simply divide both sides by 874.8. And so you get then, that goes away here. So I get the cosine of theta is equal to that angle. And then if I'm trying to get to theta, I simply apply the inverse. So after I do that, I'm going to apply the inverse cosine to what I get here. And when I do that, for this one, I get that theta is equal to 176.5 degrees. If I use the other equation that I had here, which is that the 53.55 is equal to that, I'm going to get a different equation. And on this one, I get that the sine or theta that I get out of this equation is that theta is equal to 3.5 degrees. And which one of those is right? Well, this is the one that's right. And by the way, if you try to do the tangent of theta formula that we saw in the last video, you're going to get that theta is equal to a negative 3.5 degrees. And of course, neither one of these two are giving us the correct angle, and this is the reason for that. Let's go ahead and look on that second page of that handout that you printed. And the reason that only certain angles work or certain functions work in certain places is because of the way we defined the inverse trigonometric forms. If you remember from Cal 2, when we looked at, for example, a sine curve, and I'm going to come down here toward the bottom and write this for you, but when we looked at a sine curve, of course, remember we use pi over 2, pi, 3 pi over 2, and 2 pi, and we can even go in the other direction here, and it would continue the same process. So basically, a sine curve fluctuates between 1 and negative 1, and it looks kind of like this thing. Now, if I look across the entire function, I can clearly see that this function is not one-to-one. And in order to have an inverse, that function has to be one-to-one. So what we did was we said, okay, well, let's just break off a piece of this. Now, I can't go from 0 to pi because that wouldn't be one-to-one either. Remember, it'll have to pass a horizontal line test. But if I eliminate everything here, and I eliminate everything here, notice that what I'm left with is just this piece in here between negative pi over 2 and pi over 2, and that piece is actually one-to-one. Therefore, looking back up here at my circles, the inverse sine function is going to only exist when I'm dealing with values between negative pi over 2 and pi over 2. Inverse tangent, same thing, and it was because of the way we blocked it off. In the inverse tangent, it just cannot include the endpoints. For the inverse cosine, we were between 0 and pi. And based on the vector that we just got in the last section, which was this vector here, remember it had components negative x and positive y, that puts me in the third quadrant. So the only inverse trigonometric function that I was able to use would be the cosine, inverse cosine. If I use one of these others, then I have to use reference angles. So for the sine, remember we got 3.5. Well, if you take 180 and you subtract 3.5, you get the result we got, which was a 176.5 degrees. So the point is here, you just need to be aware of what inverse trigonometric function you're using and make sure that you're using one that falls within the correct domain.